Good day, everyone. Thank you for being here today. I will present our research on a novel model, bidirectional quantum long short-term memory for photovoltaic power prediction. In a sense, we have integrated quantum computing with deep learning to address the critical challenges of unpredictable solar power, a key issue in our transition to renewable energy. As global climate change push us towards renewable solutions, Taiwan transitions to green energy relies heavily on solar power. However, this introduces a critical challenges, the inherent instability of PV systems. The fluctuating nature to solar output caused by unpredictable weather threatens grid stability. Therefore, developing a forecasting model that is not just accurate, but also rapid and reliable has become more essential to our energy security and net zero emission goals. Our primary objective in this research was to propose and validate a new model based on ByQLSTM, especially for short-term PV power forecasting. We aim to significantly enhance predictive accuracy by creating a synergy between the computational power of quantum computing and the contextual understanding of attention mechanisms, thereby creating a model that is both powerful and interpretable. The result of our work is the bidirectional quantum LSTM, as known as BiQLSTM. This is a hybrid quantum classical model, meaning it leverages the strength of both computing paradigms. Its architecture is specifically designed to process time series data by using attention mechanism to prioritize key temporal features. This ensures not only high performance but also a degree of interpretability in its results. The core of our models advantage lies in the variational quantum circuit or VQC, which replace classical processing blocks. The VQC operates in the hybrid quantum classical loops. First, it encodes classical data into a quantum state, then using a super precision and entanglement, it transforms this data within an exponentially large computational space where complex patterns become more simpler to analyze. This transformation is guided by tunable parameters data. Finally, the resource is measured and a classical optimizer intelligently adjusts the theta parameters to minimize the error. This iterative learning process allows the VQC to become more highly specialized and efficient problem solver. So let's trace the data flow within a single QLSTM cell for one times a step. Right. For here, sir, the cell receives two inputs. The previous hidden state, which is a summary of the recent past, and the current input vector, which is the new data at this moment. So first, the full forgotten gate, powered by its dedicated VQCs, analyze input to decide which information in the long-term memory is now obsolete and should be discarded. And the second gate, import gate, uses its own VQC to determine what new information from the input is significant and should be stored. And the resource from these two gates are then combined to update the own long-term memory. Uh, all long-term memory into the new current long-term memory. And finally, the output gate inspect this newly updated memory, long-term memory, to produce two final outputs: the prediction of the current time step and a new hidden state to be passed on to the next time step. Our model combines bidirectional temporal processing with dynamic focusing capabilities. This improves learning of long range dependencies in solar power patterns. The attention mechanism reduces prediction error without increasing computational complexity, giving us a better accuracy at the same computational cost. So these slides provide some more detail of our model's two key components. We see by QSTN's dual pathway structure, the input sequence is fed into two parallel QLSTM layers. The bottom one here is called the forward in time, it capturing the historical context. The top, the process, the same sequence in reverse. It capturing what we can infer from our future context. And each time step, the outputs from both layers are combined, giving the model a comprehensive, context-aware understanding of the entire sequence. And the second diagram illustrates the attention mechanism. The sequence of hidden states produced by the by QSTM is fed into another small network. This network's sole purpose is to calculate an attention weight for each hidden state. And these weights determine how much influence each hidden state has on the final prediction, allowing the model to focus on the most critical moments. And to validate our model, we use a real-world data set from a PV plant in southern Taiwan, covering the period from December 2022 to September 2023, and reported at 13-minute sampling intervals. We then benchmarked the by QLSTM against by other prominent forecasting models using four standard metrics: the mean absolute percentage error, root, mean mean square error, mean square error, and R square to ensure a comprehensive evaluation. So our model demonstrated strong and consistent performance on this real world. For example, 3 separate days in March, April, and July 2024, which represented different weather patterns. The model achieved to 2.80% mean absolute percentage errors, and R square reached to 0.99, and showcasing its robustness under varying real-world conditions. All these charts visually represent our model's high accuracy. The forecast curves generated by our model shown in blue align almost perfectly with the actual power generation curves. This near perfect tracking even during the volatile midday peak and the sharp ramps in the morning and evening confirms the model's ability to capture the true dynamics of the PV systems with a high fidelity. So when benchmarked against our models, the performance leap of our BiQSTN is significant. We achieve a 273% lower error rate than the traditional BP models. Even more impressively, its front-end was 194% faster than the powerful model CNN and LSTM. This combination of superior accuracy and high efficiency is a key breakthrough of our work, making it viable for real-world, time-sensitive applications. This table presents a full comparison across all benchmark models and metrics. It serves as the comprehensive evidence of our claims. As you can see in the bottom row, our BiQSTM model consistently and decisively outperforms the other in every single category. From the lowest error rate across to the highest R-square value and fattest CPU runtimes, 19 seconds. The impact of this work is direct and practical. For grid stability and our models allows operators to better anticipate the solar powerful fluctuations and balance the grid more effectively. For our national energy goals, it means we can rely more heavily and confidently on solar power, reducing our dependency on fossil fuels. Ultimately, this provides scalable, deployment-ready solution for the smarter energy infrastructure. So in conclusion, our BiQST model represents a significant breakthrough in PV power forecasting. We have demonstrated the synergy between the computational advantage of quantum mechanics and the context understanding of deep learning is a true game changer. This work delivers a future ready tool that is accurate, efficient, and poised to play the key role in the global smart energy transition. So thank you for the time and attention. I would love to answer any questions.